Okay, let's start. Today's speaker is Dwaipayan Majumdar, a PhD student at our university. And he will talk about Diophantine approximation with prime restriction in real quadratic number fields.
Okay,
Okay.
Thank you. So I would like to thank first Professor Stephen Bayer for giving me an opportunity to give a talk in the colloquium, and under supervision of whom I did this work. Okay, so our title says that the Diophantine approximation with prime restriction in real quadratic number fields. So let us first investigate this um, Dirichlet's theorem, which says that if we all know that if that rational number is a dense in the real numbers. So if you take a real number,
One moment. Could you make it a bit larger? Some zooming in?
okay, then I'm trying.
It's easier to read them.
Yeah. Is it possible?
Yes. Yes, that is nicer. That's better to read.
Yeah. Is it okay?
Yeah, I think so.
Okay. So all of us know that rational numbers are tens in the set of real numbers. So we can approximate any real number by rational numbers. So Dirichlet's approximation theorem actually gives a sort of quantitative study for that theorem, that how well you can approximate a number. But one thing is that so Dirichlet's approximation theorem says that if you take a irrational number, then there are infinitely many pairs p by q which are co-prime integers, such that x0 minus p by q, so that the distances from that point of the rational from the chosen point to the rational numbers is less than or equal to 1 by q square. One thing is there though, you must have an irrational number. For x0 must be an irrational. For rational you cannot get this. So Dirichlet's approximation theorem says, so it is a type of quantitative studies. Now the thing is that if we, so one question we can ask, that how well really we can approximate, that is the about what about the exponent here, what about the exponent 2 here, and there is another direction, and one may ask another question, that what if we restrict ourselves to the prime numbers when the denominator is only primes. Okay, so the problem of Diophantine approximation by fractions with denominator restricted to prime is really hard actually. And
sorry to interrupt you.
Yeah.
What is the main motivation behind considering Q to be prime? Why do we want that? I mean, it is just just for the sake of considering prime numbers, or is there any deeper reason to deeper reason to require that Q should be a prime?
I don't know any very satisfactory answer maybe, but for the prime the case is really interesting actually, because I know these primes are really discrete set. It is more discreteness is than the natural numbers. So I think it is a really interesting set to consider set of primes. Hello.
So I'm happy. Thank you very much.
Okay. Welcome. If we consider also that denominator is prime, then that actually triggered a lot of problems. It's not difficult to prove using this generalized Riemann hypothesis for Dirichlet function, that for every epsilon greater than 0, you will get mu equal to 1/3. There are infinitely prime pairs p pi, and p is an integer and pi is a prime, such that this one happens. And but an improvement beyond this actually depends on very strong assumptions on prime and arithmetic progressions. But apart from that, there are many results and conditional results, like Vinodolov did, who showed that actually nu equal to 1/5. That is actually due to his treatment of trigonometrical sums over primes. Okay, and then this Von came in into the picture and who actually used the Fourier analytic method to get nu equal to 1/4. Okay, actually, our paper actually is a analog of this Von's result uh, in the setup of real quadratic number fields. Uh, so yeah, so then Herman proved nu equal to 3/10 by his own sieve method. So Herman sieve, and then Gia and Herman also get in several papers improved the result, and ultimately Herman got 7/22. Okay. So, and Hildebrandt and Gia also brought the Kuhlstrom sums into the picture and made a number of further innovations, like nu equal to 16/49. And the latest one was by mathematics, who managed to reach nu equal to 1/3 by using the bounds or averages of Kuhlstrom sums. And that is actually that is considered the limit of the current technology. But one can expect that new can be one. One can expect that new may be one here. So, but we don't know. We don't know still now it's possible or not. Um, but yes, so Stephenson and Professor Mark Ticknow has uh, extended this classical version to the imaginary quadratic number field, and they got the same result was Herman was got for the classical setup, that nu equal to 7/22. And there is introducing the novelties into this method, in particular a clever estimation of trigonometrical sums over the regions of C, a sharp product. That is by Herman. That is by Herman himself. But the Professor Stephen Bayer and Professor Mark Ticknow has developed something called smooth trigonometrical sum, and the sharp cutoff by smooth version of Herman C to have nu equal to 1/4. That is the Bond's analog thing in uh, uh, complex quadratic number field. So that was there, and ultimately they have got this result. That is this one. I mean, uh, if you take this q square root of d minus d, so it is a complex quadratic field, imaginary quadratic field, and a square-free positive integer has class number 1. Then you can take this x0 from complex number, but not in square root of minus d, then there exists infinitely many non-zero prime ideals. So instead of primes, here we are taking prime ideals in O, the ring of integers of q of square root of d minus d, such that this happens for some generator q of p, and p belongs to O, this ring of integers where norm p denotes the norm of p, exactly what we have. So that is there. Von's exponent we are getting here, and next, so we want to construct the same thing in the setup of real quadratic number fields. But now we have two difficulties. We are facing two difficulties. One is that infinitude of units. So in the real quadratic number field, you have infinite number of units. The unit group is infinite, and second one is the counting problem is really two-dimensional. So if you actually go on, you can see that we ultimately headed towards a counting problem that is really two-dimensional, and that creates problem. So yes, but our actually, I mean, our motivation was very same as like this quadratic imaginary fields. So our starting point will be the smooth version of Herman C for quadratic number fields, where we use the formulation with ideals instead of algebraic integers. Obviously, we are using these ideals just to get rid of the problem of infinitude of units, because you know that if you multiply, first of all, we will take the class number 1. So if we take class number 1, then all ideals are principal ideal domain. So all ideals are principal. So if you multiply one unit by that, but as it is ideal, it doesn't affect the Okay. Okay. So okay, so we will just transfer everything into ideals. That was the first idea. So there are some notations. In the case of actually we are taking a particular d. D is a positive square free integer satisfying uh, d modulo 3 not 4, in which obviously the ring of integers or O is basically z of square root of d, and ring of integers of q square root of d by O will obviously that's a natural thing, and write k as q of square root of d. Um, we denote the set of ideals involved by this I, and obviously your these are two sigma 1, sigma 2, these are two maps, sigma 1 alpha plus beta square root of d, and alpha plus beta square root of d, and sigma 2 alpha plus beta square root of d is alpha minus beta square root of d. And your sigma k is your just that's that tuple, sigma 1 gamma and sigma 2 gamma, the gamma belongs to k. Okay, so we will assume here that, as I was saying that time, that we will assume that class number is 1. So all ideals are principal. Okay. So if you take a norm of an ideal, it's just the norm of Q. If Q is a generator of this curly Q. Okay. The norm Q is the modulus of the norm of the Q of an algebraic integer Q. Okay. And we will denote the DCP by CD of P cube is just a P. We are using approximation sign because there may be some unit, is up to unit here, and yeah, and you will take some variables delta n x, where the scaling inverse is less than equal to delta less than equal to 1, and these are the very big constant bigger notations, and epsilon be arbitrary but fixed positive integers. So with this kind of setup, we can announce our theorem. So first of all, we need a Diophantine approximation theorem in real quadratic number fields. As we before we have the Dirichlet's theorem, then we actually restrict ourselves to have primes in the denominator. Here is the same. So we need a version of Dirichlet's approximation theorem in real quadratic number fields. Uh, that is that one, that is by QMA. So there exists a constant c greater than 0 with the following property. If x1 and x2 belongs to R2 minus of sigma of k, and then there are infinitely many pairs PQ with belongs to O and O minus 0. So obviously Q is not 0. Both are from a ring of integers. Such that this happens, that mod of xi minus sigma I p by sigma iq less than or equal to c, and then in the denominator that was sigma iq modulus and sigma 1 q plus of sigma 2 q. But you can immediately modify a little bit, and you can find that in place of this denominator, in place of this denominator here, you can find uh, this one. C is a norm of Q. Okay, for some generator Q of capital Q. I mean not capital Q, but it's curly Q maybe, and this P belongs to O, and O prime to Q. Okay, so now we have this the version of Dirichlet's approximation theorem in this real quadratic number field, and so now we can ask what if we choose a prime. Okay, but before that, this one is required. Our case, that is good and bad x1 x2. As we go on, this will be clear that why it is required. But before, I just want to say that is so if you have chosen a tuple, right, x1 and x2, that belongs to that field but not in this sigma k, then we have by this above corollary, we have this second equation, second inequality, no? Number two inequality that is holding, but then your ui u plus v square root of d and a plus g square root of d co-prime in O, and you suppose norm of this particular a plus g square root of d is called a w. uh, then we need really this notion that we call that that pair is eta good if we say uh, this GCD of f and g. You can always get a GCD at f and g is bounded by w of eta, w to the power of eta, big O of w to the power eta. So it is a really an order of w to the power eta, where eta is the chosen number. Okay. Uh, Yes. So if you say that is good if it's eta good for all eta greater than 0. Okay, we need these numbers, and we call x1 x2 is bad if it is not good, as usual. So yeah, so our main result is the following. Uh, that is here. Assume that if you take this q square root of d again and has class number 1, and if your d is a positive square for integer satisfying d modulo 3 d is congruent to 3 modulo 4, and let epsilon be any positive real number. Suppose further that moreover you have x1 x2 belongs to R2 minus sigma k. Is eta good? In the above sense, then you can set mu equal to this fraction 1 by 8 minus eta by of 1 plus of eta, but 1 plus of 2 eta. Then there exists infinitely many non-zero prime ideals go in this ring of integers go such that this happens. This modulus of xi minus sigma I p by sigma I q is less than or equal to norm p, the minus half and minus nu plus epsilon for some generator q of p. Okay, and if x1 x2 is good, then you can actually take nu equal to 1/8.
So, Dwaipayan, can you once again explain the definition of eta good?
Yeah, sure. So what happened is that by this polar decree, actually, we have we have this kind of less than equal to part. Okay, so now if you take this p equal to suppose u plus v square root of d and q equal to f plus g square root of d, then you are getting infinitely many this kind of numbers, right? That is what it is saying.
Yes.
Now the thing is that always you can find a density for f and g. Okay, so now what we are demanding that to be good, to be good, this density of f and g is equal to the order of w to the power of eta. That is what we are saying, and I mean it is bounded by some power of its norm.
Okay. Infinite sequence of natural numbers that
Yeah, what's that?
holds with n norm.
Hello.
Yes. Yeah. So two holds. So this inequality holds if with norm of f plus.
Hello.
Right. Yes. Dwaipayan.
Yeah,
So
is it okay?
natural numbers that holds explains. I see.
Mhm.
Yeah. So it other games. Okay, now it's fine. That's fine.
Okay, thank you, sir. Right. Uh, Okay, so yeah, so now we are as we have already earlier said that we will follow a smooth setup, and but here is something that a smooth setup when you are doing a smooth setup when you are involving something summations and all kind of things that will appear very soon. But then you need to understand two things. You have to keep two things in mind that whenever you have summation, you need to confirm its well-definedness and also its convergence. It is convergent, right? Uh, and uh, and due to the case of infinitude of units, there is a little bit of trouble. We are therefore shifting this actually summation to these ideals. This thing will be clear if we proceed. So what we are taking this throughout the sequel, that C be a natural number, which will be fixed in the course of this article. Actually, put out this of this total talk, and we will later actually choose C properly to have a bound. Okay, and we shall make this non-negative function fx that is some sort of differences of Gaussians to the power of c, okay, which has on one hand exponential decay as mod x tends to infinity, and satisfies on the other hand we have the bound like fx less of c minimum of plus 1 and if mod x to the power twice of c. And also one idea is that whenever we want to prove that we are wanting something here. So one idea is that if you take this as a delta for the time being, just take this delta, this non-p part, and come back here, right? So you have this x. For this x part, we just take that particular part here on the left hand side. Now you observe that your delta square in this 5, your delta square is larger, larger than x. If it larger some and some power of x, then it is actually uh, it has an exponential decay, so it is really uh, really small, very small, negligible, right? We will use this actually. We will use this idea here. That is, now for the time being, is just take this delta, omega of delta of x is actually exponential of minus pi, dot x square by delta square, and then we define two functions. These are the weight functions here, and observe here once more that we are taking this into an ideal. So your weight functions are omega q, so q is an ideal, small q is an ideal here, and delta square by 2 square root of 2, and we have psi of q, and omega tilde of q is equal to psi tilde of q dot fq, where your psi q equal to just this one, the summation. So what we are taking this, so we are taking all such k from the ring of integers, and such that this k will generate q, and we have this f of sigma 1k and square root of norm, and f of sigma 2k by square root of norm, and psi tilde q is same as psi q but with a sort of scaling. Okay, so n by norm q, this is a scaling part, so we are scaling sort of. Okay, and your fq is actually defined as, that is summation. Okay, this is taking the summation, and p belongs to O as a ring of integers. The summation runs over the all elements of ring of integers, and this omega. So in the place of capital delta, uh, you are taking small delta by square root of n, and in the place of x here you are taking x1 minus sigma 1 p by sigma 1 q. As just as I was saying that we will take that actually eventually. So that was there. Okay, so yes, and q is your one of the generator. Any generator you can take, okay, for the q. Uh, so yes. Now, first of all, as we have to check is whether this omega q and omega t that are well defined, but these are well defined actually. You can see these are well defined. But moreover, we have one more thing that is important is to show that if q is well defined, it's more. If you take a unit times of p, then you can see that this is any generator I am saying. So it may happen that another thing is that u of some unit times u of q, u is an unit. But if that happens, then what you will do, we just do this q. So this is your q and u here. So just now in the next step, you just break this down. That is sigma 1 and q and sigma 1 q, and then this particular sigma 1 q, we just move to numerator. Okay, by inverse, as it is a unit, we have an inverse. So just do that, and again, as p goes over all the ring of integers, this fq making sense. Okay, these are well defined, and not only that, these particular functions have some sort of bounds. That is, fq is equal to less than 1 plus delta square n by norm q. Okay, and moreover, we have psi q and psi tilde q have some bounds like exponential of minus pi d c of norm q by n and log n. And for every ideal q from this non-zero ideals, for every non-zero ideals, and suitable constant greater than 0. Okay, and also it has a lower bound, less 1, if norm this norm q is in certain range. Okay, and then also we have this weight. These weight functions have some bound, like omega q is less than delta square exponential of that log n, and omega delta q is exponential of that. Okay, it has some bound like that. Okay, having said that, now just let me just tell you what is the idea is. Now we are taking the summation. Okay? We are taking the summation of omega tilde p, or this capital T tilde of n, and that sum runs over all over the prime ideals, non-zero prime ideals, and you can establish the convergence by these bounds for T. Okay, you can establish the convergence there. And now, what does it measure? Okay, so the above quantity you can see it measures up to units, obviously. The number of prime elements Q belongs to the ring of integers with norm of size about n. Because if not, then you have very negligible type of quantity. Remember that your omega tilde q has actually involved psi tilde q, and psi tilde q also involved this n by norm q. So you have to choose your norm q in the size of n. Otherwise, you are getting negligible things. Okay? So yes. So yeah. So up to units measures the number of prime elements q from the ring of integers with norm of size about n, such that moreover it involves this kind of fq, which is again if you go more than delta by square root of n, you are getting due to have some exponential decay, you are getting negligible things. So ultimately, as a sum up, is actually getting the number of prime elements q from the ring of integers. The norm of size is about it, such that this particular distance xi minus sigma I p by sigma I q is not much larger than delta by square root of n for I equal to 1, 2, and a suitable prime p belongs to. So now our approach is just about the Herman's philosophy, that we will compare a known thing to a known thing, and actually Herman's is also based on this, and our known thing is this one, this capital Tn, right? And capital Tn is actually this omega p, where this p runs over the prime numbers, and again prime ideals, not prime numbers. These are prime ideals, non-zero prime ideals, and this quantity Tn measures up to the number of prime elements q belongs to O, and norm of size about n, scaled by a factor, something like that. But that is a kind of known thing due to this Landau's prime ideal theorem, and we obtain this Tn tilde is equal to delta square n, delta square by n by log n, and we will use this 6 and 13. Okay, this is that lower bound thing we will use, and also 6 we will use. Yeah, that was omega q. Okay, so it functions, and this lower bound together we can find out that that Tn has sort of this lower bound. And now what you will do later, that if you are able to show that this difference t tilde n minus tn is very much small compared to delta square by log n, then we can yield that about lower bound. One can yield also lower bound for same kind of lower bounds for t tilde n, and that is required for our theorem. So we will establish this theorem 6, which says that if you x1 x2 are belongs to uh, R2 minus sigma k, which is eta good, where eta is greater than 0 and epsilon is less than 1 by 14, then there is infinitely many natural numbers n, such that t tilde n minus tn is just less than delta square n into 1 minus epsilon. So hence t tilde n is greater than delta square dot n by log. Okay, we must have some range for delta, and that is delta is less than equal to 1 and greater than equal to n into minus mu plus 15 epsilon. Okay, and mu is chosen to be like that. That is a latter part, but the idea is this one, to have a lower bound, okay? Because in our mind we want to show that this is infinite kind of thing. Okay? Yes. So if x1 x2 is good, then and we can choose, we can make our eta as small as we wish. So ultimately we have all things are okay, but in the place of mu we can just use 1 by 8. Okay, 1 by 8 plus epsilon sum epsilon is there. Okay, again some important lemma. Okay, this first important lemma is very important because it actually depicts you that if you have a number sigma, if you have an element from ring of integers, then we can consider two numbers, right? Sigma 1 of that number. Say suppose m or m naught is a member of O minus 0, non-zero element of ring of integers, non-zero element of ring of integers, then we can choose two numbers, sigma 1 m0 and sigma 2 m0. So this lemma actually depicts that there is always a unit is an universal unit. If you multiply with this m0, then you are in a sort of range of square root of norm. Okay, we have used this lemma in many places. In fact, more or less all places to have some sort of I mean everything. In the case of also this bound for these functions also. Here we have bound this function fq and 11. For getting such bound, we have used, and in many cases type 1, type 2 sums everywhere we have used this. Rather, the second lemma is lemma 9. We have used somewhere, but I think I can, because that proof was really big, so I'm not going to prove that. So I just leave this lemma 9. It is not required for this talk. Okay. Now, as we know, this is the very common trick for number theory, analytic number theory. When you are introducing the smooth summation, smooth setup, then what you will do, you will use Poisson summation formula, and then you will cut off that. Okay, you will cut off your suitable range and then take the negligible part. So here is also the same thing. So we have this Poisson summation formula here. Okay, this is nothing new. It's just the ordinary Poisson summation formula for Ra. In our case, we are R2. And if you use this Poisson summation formula on this FQ, then you will get this one, this 17. Okay, that is, and we work on that, and our omega tilde q is then just if you put this FQ in this omega tilde q, then you will get it this one. Okay. So far that's good. Now you will just take the differences. If you take the differences, omega tilde q minus omega q, then you will get that this one, this 19, and this will be used in our type 1 and type 2 sum. Now I am coming to that what is type 1 and type 2 sum. So in the case of Harman sieve, there is a setup, very ordinary sieve setup, that is all. But in the case of numbers, we are using ideals. Okay? So this is the non-negative real numbers. If you take K is obviously quadratic field of ring of integers, and all kind of this. Important is this P. The P is a your set of all non-zero prime ideals of it, and we are taking Pz to be the all such prime ideals, but which has no is less than of set, and Pz is the product of this, and dk of this ideal, actually the number of ways to write an ideal is as a product of k ideals. So d2 of A is simply the divisors, number of divisors of ideals of A. And in the case of GCD, two ideals is a co-prime. So this O is the only divisor of both A and B. Okay. Now what is the sieve result? Sieve result is a very big, so I just want to do a little bit of cutoff. The thing is that whenever you have to weight functions, and your weight functions satisfies some relation like 20, okay, where x is greater than 1, and moreover you have here is the some kind of comparing it, this is y is greater than 1, and your mu is 0 to 1, and kappa is 0 to less than equal to half, and m is in between this open interval x mu and x. Then if we have complex numbers, the sequence of complex numbers which satisfies mod of A alpha is an ideals less than equal to 1, and B of this particular things are less than equal to divisors, number of divisors of B. Then if you have this one, T1 is actually, we call that is a type 1 sum. Here is only depending on this norm of A less than equal to M, and only we have A suffix at ideal A, and that is less than equal to 1. And type 2 is equal to, we have some in range x mu and x mu plus kappa, and then we have E of this ideals in the suffix A, and this BB, this one, and this also is an equal to K. It is equal to Y, and then we have this kind of 23 kind of inequality, where your S omega Z is obviously this kind of sum, this summation of all W of A, this is WZ basically, is equal to summation of all W of A belongs as ideals, and A and P is equal to 1. So all such co-primes. Okay, this is our sieve result. The thing is that now we want to connect this our P, what we have previously defined, P and P tilde, to this. I mean, where do I define this? I mean, this P and this P tilde. Okay. you want to and to connect with this one, h omega x kappa and h omega t x kappa, and that is very easy. If you do a little bit, then you can see that considering this delta is in this range, and m is the ceiling function of x of 1 minus epsilon, m is at 8 to twice of x of to the power 1 4, and also you can choosing that dk of q is equal to less than equal to mod q to the power epsilon if mod q is large enough. Then actually we can establish 24 and 25. Okay, all this, if you take this, we can establish that it actually set up the bridge between s omega x kappa and tn, and that is required for us to prove this one. Now, if we go for type 2 sum, we have to use this type 2 sum, which is which is
How are omega and omega bar defined?
yeah, what sum?
Omega and omega bar defined?
Yeah, omega and omega bar we have defined because these are the weight functions. The just yes, fine. These are the just weight functions. That is that one 6 and 7. So we have site in the queue and hello.
Okay, yeah, I see. Correct,
Yeah.
that's correct.
Okay, just let me finish that. Yeah. So whenever we have this, now we will set up that one and. Yeah, now we'll do the treatment of type 2 sum, and type 2 sum is we have uh, marked something, we have taken some smaller definitions like EL, exponential, that is the Gaussians, and this curly of EL is this exponential things, and GK is your uh, that particular uh, f of sigma 1k and square root of n, and f of sigma 2k square root of n. And if you really observe this type 2 sum, you will understand that it's ultimately it looks like that. Okay, and we will take k is any generator in the second line. This k is any generator for this ideal m and n. So this summation in our case will be sum of our ideals, and if it, I mean, after that the generators, we are collecting the generators that k equal to k is a generator of ideal m n. And now what happens is, again, as I have said already, that we will use this lemma it on and on. So the thing is that we will choose every generator m of this ideal capital M in the range of norm of square root of norm of m. Okay, and also if you use the definition of the psi of mn is independent actually, the sum over p from the choice of k as generator of mn, we write this uh, for mn, for m fixed, we now fixing this m, and we will set this n equal to k by of m. And now we unfold the sum in belongs to I belongs to, and summation of this one. So what happens if there is any unit is occurring here, we will shift this unit to the in part of n, because you observe this our second sum, this one is running over all ideals taking this n. So unit we can throw that unit part there. So only this your m actually depends on the risk. I mean, this maximum, what we call this maximum system of mutually non-associated elements of m. So they are not associated mutually. So if you take m1, m2, there is no unit such that you can write no unit u such that you can write m1 equal to u m2, and also norm of m is in the range. Okay, so taking this one, we are your type 2 sum becomes like that. Okay, and ultimately, as we have said before, and we have something probably we have also depicted this. We have taken this f part actually inside, and we rename it by ep comma k, and that is that. Now, as I have said also that the general technique is to cut off. So we are here is we are cutting off this summation. That if you this norm your floor function ceiling function of x to the power 1 minus epsilon, and if you choose now we are using this c, which is and the very fast definition of f in the case of smooth setup we have depicted c. Now we are using it, and if you use it, then we can find out this summation is really negligible if this happens, this 27 happens. The maximum of sigma 1 and sigma 2 n is less than equal to square root of x by norm n, And also P also happens like sigma 1 to P is less than or equal to x to the power epsilon into delta inverse. With this particular cutoff, okay, we are again we have this range and we have something big O of h to the power minus 100. Now what we have to do, we have to now take this. We will divide this uh, interval of norm n into the m sum into this. I mean, divide the m sum into this p go log x. Actually, this is we are doing this. We are dividing into these dyadic intervals, right? So we have at most p go log x subsums, and then we are taking for each particular part we are taking the suprema. Okay, so sigma k, your sigma k is actually showing one part, and is sigma k is that, and if you use this one, and after something just you have to expand everything here, expand this if definition and all everything, actually you will get uh, this thing actually here sigma kg. Just let me just not that exactly. So from that you have the sigma k will be coming into that one, and if you just expand this cth power, so there is an 8, there is a cth power, if you expand that, then you will get this kind of big fellow. Okay, here j1 and j2 comes in, and you need to tackle this particular ejpk here, and now at this position to this end and the 29, we will focus on this delta and sigma of k of j, capital K of j, I mean this particular sum. Okay. So then in the case of type 2 sum, we will actually removing the exponential weights, and for that we will use this inverse Boolean transformations, and the inverse Boolean transformations is nothing but this one for Gaussian. So we have a lot of Gaussians here. So in each case you will use this Gaussians, okay. And then what you will get is again a big fellow is coming. If you put this all together, your sigma k's will be that. And if you focus on sigma k's, and we will consider this kind of bounds, I mean this kind of bounds here, and c of 1 by log x, and in inverse is less than equal to delta this. Your sigma, I mean phi s is big O of 1, then this particular phi s, this one is becoming big O of 1, and your A index becoming less than, I mean, is bounded by some constant, same as for, so BNS is also, I mean, it's not bounded by some constant, but it depends on n, it is a divisor of number of divisors of n, the ideal generated by n, okay? And CDS1 is this one is also big O of 1. So with this kind of bounds, we actually.
Dwaipayan?
Yeah.
I just want to remind
Yes,
you
sir.
to the time. It's 15
Yeah, yeah.
minutes left only, so you
Okay.
keep that in
Yeah,
mind.
yeah, I will. Yeah. Okay, yes, sir.
Okay.
Thank you. So now what we will do, we will do this Cauchy-Schwarz inequality. We will use that Cauchy-Schwarz inequality, and ultimately for this Cauchy-Schwarz inequality, if you use this Cauchy-Schwarz inequality, you will get something like that. Okay, in this sigma case s square and that one. Okay, so ultimately, if you again this, if you remove this particular part and the summation and to as mod, and if you open it up, then you will find out a little bit of this one, sigma k square and that. And now again, you will use this Gauss summation formula for this one, and then actually we're getting something where we are actually heading towards a counting problem. Okay, and this counting problem actually says that this particular setup. Okay, we will use a counting problem first of all, and also here we are using this graph and Dirichlet's approximation theorem for QD for this, and this then your sigma k s square is simply coming like that one. But chi j is the characteristic functions on the intervals minus delta tilde and delta tilde. This particular norm-like things basically the smallest integer distance, and norm of x is nothing but minimum of modulus of n minus of x, where n belongs to set. And then if you take theta, your A by W, B by W square dot D, and if you adopt this notation, then actually you are getting this one, and ultimately uh, you are getting 38. If you just multiply with this, you will get this particular distance with this, as C stands for that, and this lambda and mu are certain range. Okay. So now the important thing is there is a important relation holds between A and B. If you write down this theta carefully, b plus b squared of t by b plus g squared of t, then you are getting something like that, which is x squared minus b squared t equal to 0 modulo w. And now we will heading towards the counting solutions. So we observe that we need to detect that particular relation, that A lambda plus BT mu equal to modulo alpha, I mean congruent to alpha modulo W, and B lambda plus A mu is congruent to beta modulo W. And if you just little bit of multiplication and subtraction, you will get this B alpha congruent to A beta modulo W. And then you have to count. So what is the idea is basically we count firstly the pairs alpha beta lying in the relevant range, and then you fix alpha beta and count how many pairs lambda mu in satisfying the relevant range. And after fixing alpha beta, assuming that lambda 0 means there is a particular solution, you will see this 43 actually looks like that one, where if the solutions are the form is lambda 0 plus lambda tilde and mu 0 plus mu tilde. So you just rename it, and we just taking the lower equation and throw the other equation out. And if we do this one, and ultimately we have a condition like that, that is B capital B modulo of AF capital A modulo W, where A, B are in certain range. Okay, and you can get the same shape for other one V also. We did for one mu, and you can do for V also. Okay, so there are two variables, 2 and V. So and they are in the same shape. So we are ultimately in 49. Okay. Now you need to detecting the continuous classes using the additive characters. Here is the problem begins more or less, because now you suppose under the condition that A z prime being equal to z b prime and w equal to z square w prime, GCD of b prime and w prime equal to 1. Um, we will actually estimate that one. We will actually estimate this particular thing, theta x a b and colon w, by either one of this 50 or 51. Where 51 is depicts that if a equal to z of a prime, b equal to z of b prime, and w equal to z square w prime, and this is twice a prime w prime equal to d prime, and d prime is a divisor of 2d, and this kind of notation, this kind of um, 50 or 51, we always actually come back to this one. And also this a square minus b square b equal to 0. I'm sorry, modulo x square is converted to b square b modulo w prime. That will happen too. Okay, that we have established. That one thing is here that you can see already, that this is happening once, and we just take this, we just throw out this z and take this one, and another one is this one is happening. In the same case for the 51 too. Okay, so there is no harm to considering just taking 50. This 50 equations, and uh, we will do with 50. We will work with further 50, just assuming this 50, and using this exponential additive characters, you can actually bound this sum, and the bound is looks like, and for the bounding, actually for this bounding part, if you use this lemma, that if your gamma can be in this range, gamma minus u by r is minus 1 by of r squared, then we have that. Okay, we will prove that yes, this is indeed the case by this. This is a very interesting part of that. We will use a Bullish paper to say that this congruent relations. Congruent relation means this gamma, this a prime b prime bar by w prime is indeed satisfying some kind of these relations. Moreover, your w prime is inside. It's in the range of r. I mean this r is basically not w prime. In other words, you can say r is in the range of square root of w prime. So we have this kind of result because this kind of estimation is is there provided we have a Dwaipayan approximation like that. So we can prove this, and also we can prove that this R is basically is in the range of square root of W prime. So it is a very interesting and very new part of our paper. Obviously, it's an interesting part of our paper, and with this actually we can go uh, like that. This is the estimation 61. Okay? And ultimately, if you all put together, then we can find out this sigma k s squared is 62, and provided W has some bound like that. And now we have to go some kind of back because they need to find out sigma kj, and the gamma factor. We bound these gamma factors by Starling's formula. I just want to remind you, due to using this Melling's inverse transformations, we have some gammas in our removing weight part, but I mean, uh, this gamma part is yes. So we can have sigma kj is equal to that. We can really have that. And after that, if you use this change of reversal of role, that is in place of m you put n, and in place of n you put m, then you will getting an estimate of x by k in place of k. And we will always choose the minimum one, and ultimately with this mu and kappa satisfying this relation, we will get 64. Exactly, this is the lemma. What we want to say that what we establish that if let d greater than 1 and be an integer which is not a perfect square, then there exists a positive constant c1, c2, c3, only depending on d such that the following holds. If q is a positive integer and x is a solution to this quadratic equation, then we can find u and r, which are integers. The digit is 1 such that this mod r is in the range, and we have this kind of relation holds. So in the place of x square, we have something a prime b prime power square or something like that. Okay. Okay. Now there is a proof. Why is there? So I'm not going to that because due to the time, um, I'm not going to. It's one thing I would like to mention that you cannot. There is a version available for simultaneous Dwaipayan approximations, but then you can get this kind of result. But the main problem is neither it depicts any kind of relation between W and R kind of relations that is in the range of square root of Wi, something like that, or neither it captures that uh, important relation s square minus b square d modulo c. The s square minus s square is congruent to b square d modulo W prime. It doesn't capture that, so you will not use it. Okay. So there's an reducing point. I'm not going to that. After this, after all such calculation, if you put capital delta equal to c by W, then you will get really this t second. And also you need to now assume that it is a good pair, and then you have proved something 75. Okay, so ultimately your type sum would be um, less than this particular 75. And now you can ask that whether is there any good pair. So yes, we have in the paper we have actually constructed a good pair by the theory of uh, uh, continued fractions. We can produce a good pair, and for the record, I mean, we know to prove that almost all x1, x2 are good. That is, the bad set has measure 0, and that is also can be proved. First, we prove that given eta greater than 0, almost all x1, x2 belongs to R2 minus sigma k eta good, and then almost all x1, x2 are good. It's just a simple trick. You just take g equal to, if g is your good set, then you take this intersection of all such g1 by n equal to 1 to infinity. Now take that complement, it becomes union, and now take the subactivity of measures and use measure, and you get 0. Okay. Now the bounding of type 1 sum, that is more or less same, but there are two major changes. One is that you need to now don't remove that exponential part. Rather, we will use the we just yeah, we just use the Post summation directly without cutting the n summation range. In the previous time to that to sum, we have cutted the summation n into some ranges, but here we are not doing that. We are just keeping this n summation intact in summation range. We are just using this post summation formula, and then we are getting something same way, and using this post summation formula again. Actually, we are in the same sort of counting problem, and you use this counting problem, and the problem is ultimately if you use this counting problem, this problem is actually this k inverse, right? This k inverse is coming. But the problem is for the small k, you cannot beat your correct bound. It is really it can be it is a problematic part because k can be large and k can be extremely small. For the small, we have large values, right? So what we will do, we will exclude this small k. We will exclude the small k, and the process is same more or less. Again, we will do the same thing. The same this approximation has been used, and we will actually exclude the small k, and we are actually then come back to this d of I and that x to the power 13 epsilon and this one for eta good, and this gives a final bound like 88. Okay. Now the conclusion part is we can show by so this equation is that omega tilde and all omega q and omega tilde q. Uh, then then one can really prove this particular thing because it is required to use this normalcy by partial summation formula. We can prove partial summation formula. We can use this one. And if you combine all those results, you actually getting this one. That is required. That is our theorem 6. If you see, multiply all this, actually what we are doing now basically, we are optimizing. We are optimizing our parameters, what we have chosen before. And in that particular part, if you take recall everything and prove that, you will find out this. If this holds, delta is greater than or equal to n, and mu is your minimum of that, minimum of all kind of that is coming. And now a bit of unsmoothing is required. Because why unsmoothing is required? Because as you can remember, that is for the unsmoothing part, what we have done in the case of this, let me remind you that's we have a bit of smoothing part here. What you have depicted is FQ part. You're in the case of omega tilde q, this is involved FQ. So now you need to unsmooth it. You have this. To have this one. So what you will do? We will do this. So yeah. So there is something x1 minus of sigma 1 p and x2 minus of that. But you know that is in the case of measuring the area, we don't need the linear change. We can remove that, and ultimately we can take this one, and you can see that this we have a fundamental parallelogram whose area equals to that of this, and length is obviously using that lemma 8 actually in the range of 1 by square root of norm q. So if norm q and delta is in this range, you will see that we know this. Please recall that if q has some bound like delta, if q is 1 plus of norm q by something and delta square by n type of thing. But with this kind of range, that becomes negligible, right? And also otherwise, if it's bigger than that, then you would export due to these exponential things, you have a very negligible things, so you can cut off that. So yes, so then taking into account the exponential decay of this particular function, we have that, and if there is a p such that this, otherwise f is negligible. Okay, so now you recall this t tilde n by log n, and then ultimately you are getting that dominated by the number of prime ideals. Okay, this dominated by the number of prime ideals p belongs to I minus 0, satisfying this is now p is equal to n plus of 1 plus epsilon. Okay, so yeah, so for some q generating is provided that is so yeah. So I have already said that. So and this epsilon, there is some particular part is delta is less than equal to n to the power minus 2 epsilon, but we can choose without loss of generality. Okay, so we can there is nothing much of that. So ultimately, this together we can form this number 6. Okay, corollary 7 implies that only redefining the epsilon. So that actually concludes the proof that there exists infinitely many. So you have something which is unbounded in your lower term. So there are infinitely many primes like that. And in a recent paper by Professor Stephen Dwyer, Professor Mark Techno, and me, it has been shown that nu can be chosen with theorem 5. This can be actually taken as nu 77 by 44 minus eta plus 1 plus divided by 1 plus 2 eta. And the good pair our nu can be chosen. And for the good pair, nu can be chosen 7 by 44. Yes. So yeah, thank you. I'm sorry, probably I was a bit hurried the last particular part. So, hello,
Yeah, thank you very much for your nice talk.
welcome, sir.
And yeah, no, it was okay. I mean, it was clear you needed to finish the talk. Yeah, are there any questions? Okay, good. First of all,
So,
yeah.
okay.
Are
Thank
there
you,
any
everybody.
questions? Any questions from the audience? Yeah, so this work involves a lot of complicated calculations, of course.
So the main thrust of your article is to generalize the affine approximation to the Gaussian number field.
Yes. Yes, that was done by probably first of all Professor Stephen Bayer, and then there was a paper by Professor Stephen Bayer and Mark Techno that is in the case of complex quadratic number field.
So what are the achievements in this work?
Yeah, I think that was the same as this current paper that is in the 7 by 44. This is very current thing. That is new. It's also true for this imaginary quadratic number field too.
You should mention Harman's result. So he proved this same result, 7 over 22 or 7 over 44,
Yes.
corresponding thing, for
Yes,
Qi.
Yes.
And so we had a weaker exponent on fourth and made things work in such a way that we got, the generalization of Harman's result for all quadratic number fields of class number 1.
So Harman is already done for Qi.
Yeah,
Yes,
for
yes,
Qi.
yes.
So what are your future plans?
My future plan, our future plan is actually to achieve this mathematics result. I mean, she got 1/3 for the classical setup. So what if we can get that in the case of imaginary quadratic number field?
Okay, all the best. It was very interesting talk.
Thank you,
But
sir. Thank you.
as Stephen remarked, it has got it's got some good deal of computation. So on one thing, this is quite creditable that uh, you are on top of all these difficult calculations, and at the same time, it is also making the talk a bit complicated.
Yes, because I'm also due to this time constraint, I can't finish the proof there. But I want to mention two things. That is, one is the dealing with that infinitude of primes. That is the first one. That how we are taking this weight functions. And second one is the counting problems and that Hulis paper. That is W prime. I mean, this R actually is in the range of square root of W prime. That actually has some optimal things we are getting, the optimal bound.
So yes, but you can. My best wishes for getting some good results in that direction.
Thank you, sir.
Yeah, it's generally a challenge to, so when there are so many calculations, to explain them in such a way that it is understandable for the
So what I'm saying is that
wide audience. That's really
it will be a good idea
Mhm.
if Dwaipayan could share his slides with the audience.
Yeah, I mean,
Dwaipayan could share his slides, the PDF of his slides, with the audience.
yeah, I mean, how to share that I don't know. I can send to Stephen sir, then sir can mail that. But
You can download the PDF of your slides,
okay,
and then you can send to Stephen sir, and Stephen sir can
okay.
forward to the audience, all of us. Right? That will be good.
Okay.
Because
Yes, we can do that. Mhm. Yeah. Are there other questions? Maybe I make one comment. So there was this constraint with the good and bad pairs. Conjecturally, one should have that all pairs are actually good. But that's hard to show. That depends on very strong results about conjectures about primes and arithmetic progressions. But in the setting of the field Q square root D. So it's reasonable to conjecture that actually all pairs are good. What we have shown is that almost all pairs are good, and we have constructed some concrete good pairs. Yeah, so that I could make some more comments, but okay, that's fine. Mhm. All right. Yeah, thank you very much again for the
Welcome,
nice
sir.
talk. Mhm. All right.
Thank you, everyone. Thank you very much.
And yeah, so in a few days, I will announce the next talk, which will take place next Friday. Okay. Thank you all for your
Okay.
kind attention and see you soon. Bye bye.
Bye, sir.
Mhm.